Welcome back, Math 170. In 2.5, we're going to go over arguably the most important rule of Calculus 1. It's really powerful. It allows us to take derivatives of functions that are compositions. So if we remember in chapter 1, see if I can review, this is function notation for a composition of two functions. Now, sometimes they use it in this format, or if we remember, we used to see it in the f of g of x format. And the important part about utilizing the chain rule is to make sure that you're understanding who the outside function is and who the inside function is. So if you remember from chapter 1 or even your past math courses, we always kind of looked at the notation. It's a little more clearer when it's in the highlighted version of it. We could kind of see when you see f of g of x, the f is on the outside and the g of x is on the inside. And so just so that we can make this clear, sometimes the notation is a little bit tricky. So I always like to explain it in English first, and then we can see what we can do. So right here, we have the derivative of a composition of two functions, f and g. So that should be equal to, the way we're looking at it is f is the outside function. So this part right here, if we're going to explain this in English, let me change that color. I always like to color code to help me. When you see this f prime notation, well, it is a derivative, but it's the derivative of the outside function not just the derivative of the outside function, it's evaluated at g of x. It's a little more practice with function notation. Now, once you're able to do this, we're not done with the chain rule yet. We're taking the second part, we're going to multiply it. I know it's hard to see within the notation, but it's multiplied by the derivative of the inside function. So what I like to see is basically when I have a chain rule, I'm looking for functions within functions. And the idea is you're trying to make sure if you're going to take a regular derivative from the past few sections that we've been dealing with, we've been just dealing with if you have a single x in the argument or a single x in the base of something. So a lot of times when I'm viewing examples, example 1 will be a good way to kind of describe this idea, is I'm going to look at what's happening to each of the functions, and I'm going to try to understand, do I have a composition or do I just have a regular function of x? So if we look at the difference between part A and part B, and we can look at C and D as well if you want to all at once, I like to point out that when you look at part A, that's f of x equals sine of x, here, no chain rule would be needed and the reason is because you have just a function of x. I mean, you could kind of use the chain rule, but if you end up taking the derivative of x, the derivative of 1x is the coefficient, it's just 1. So the chain rule wouldn't really matter at this point. So I guess technically we're using it, but we never thought of it that way before. So if we were to take the derivative of sine of x, we'll review from the last section, is cosine of x. So we're good. Nice. Very, very nice. Now, what we end up having an issue with is sometimes the arguments or the bases are more complicated. Could be radicans too, but I'll go with this for now. We end up having something that might be more complicated than just a single x. And if it's in the slightest more complicated, I know if we were doing linear functions, x and 5x, not too big of a deal, but I consider that more complicated. So this is where I would utilize the chain rule. So I'll write that down. So more complicated. I guess that's my language, so be careful if you're describing this to someone else. More complicated than just a single x. So if that's the case, we need the chain rule. So if we're going to do this, we kind of have to think about who's the inside function, who's the outside function. And you can kind of use the notation F and G if that's something that you're into. I always found that that kind of gets a little confusing to me, but feel free. You could kind of think about, well, what is the derivative of sine of something? So we kind of understood from part A, if we're going to find the derivative of sine of something is cosine of something. And when I keep saying something, it's because we have more than just a single x. So we would use the something. So derivative of sine is cosine, but make sure we're using the same argument. But then the chain part, the little link we're going to add on, it has to be multiplied by the derivative of the inside. And the inside function, if we want to label it just in case, the inside function is 5x. So the derivative of 5x is just a 5. So there's the chain rule in effect. Sometimes you want to clean it up a little bit. A lot of people like to put their factors in front of the trig function. So we would have 5 times cosine of 5x. So derivative of outside function evaluated at g of x, that's why we're using the 5x over again, times the derivative of the inside function. So if you know the derivative of the inside function, that's what we're multiplying it out. These kind of take a little while to think about, so take your time. I'll walk you through a few more. I always like to incorporate trig in here just to kind of keep our trig skills up, our trig muscles, so we say. So let's look at part C and part D, and you'll probably start recognizing things start to get a little more exciting. So if I'm going to look at f of x equals sine of x squared, this is again another caution. Notice that this is more complicated than just a single x. So if we're going to take the derivative, I have f prime x. So we always ask ourselves, okay, the outside function is sine of something. The derivative of sine of something is cosine of something. And the something that we're talking about right here is the x squared. Now what we need is we need to multiply it by the derivative of the inside function. So if you're kind of thinking off to the side, the inside function is x squared. And if you're going to take the derivative of x squared with respect to x, that is 2 times x. So we want to clean this up just a little bit. A lot of times we like to put the factors that are linear outside or in front of the trig function. So we should have 2x times cosine of x squared. That's our derivative. And we just keep practicing. This is how we get better at this. So I keep kind of playing with the sign just so I get the hang of it. These things will change, and you'll kind of see in your homework, you'll have a lot of time to practice. If we're going to take the derivative of part D, so f prime x. The first thing I notice is I have a composition of functions. and I notice the argument more complicated than just a single x. So I kind of can name, if I want to, I can name this outside and the inside. In this case, my inside function is cosine of x. So before I go into the derivative of the inside, we have to figure out what's the derivative of sine of something. So the derivative of sine is cosine of something. And remember, that something happens to be evaluated at g of x. So that's our inside function. Looks a little strange. So we have the cosine of cosine x. Now for the chain part, we're going to multiply it by the derivative of the inside function. So if you remember, derivative of the inside function, we have to look at derivative of cosine, and it is not just a sine, but a negative sine of x. And at this stage, we have to be careful not to confuse the argument with the factors. So remember, whenever you have a trig function, you say cosine, everyone asks cosine of what? And so in our case, it's cosine of cosine x. So that means, you know, a lot of people will probably rewrite it so that the sine of x is multiplied by the cosine of cosine x. A little more complicated as we go. And that's our derivative. So we keep going. And remember, if we're having issues here, it's usually because we're a little bit shaky with the 2.4 material, 2.3 material. So take your time. You want to make sure you're really good at that before you jump into the chain rule, because it could get complicated in just a matter of seconds. So it doesn't hurt. I mean, I know it feels like it's more time, but take more time to really understand how to take the derivatives of functions in just a single variable of x instead of a composition. And then you can move on to 2.5. It will come a lot nicer. So let's push to part E. I'm just obsessed with sine today, so we'll go with it. And a lot of times when I see the signs in terms of sine square of x, it might be worth rewriting before you start to think about who's the inside function and who's the outside function. So I kind of like to look at the powers. Instead of sine square of x, it's the same thing as saying the sine of x times the sine of x, which is the sine of x squared. So now what we're looking at, we have to kind of look at this a little differently. We do see that the argument of sine is a single x, so that's good. But the issue is not the sine of x, that's not the composition. We're actually composing a quadratic, a squared, a power of 2 with a sine. So if we're going to start to name the inside function versus the outside function, I'll kind of point to this part. The base is more complicated than just a single x. So when I'm trying to understand to take the derivative, if I'm trying to take the derivative of something squared, I always like to rephrase it. I talk a lot to myself in my head when I'm doing my calculus. Don't feel bad. So if I'm trying to take the derivative of something squared, I do know it's 2 times something. And so we're evaluating it at the inside. So 2 times sine of x. But then if we're looking at who is the inside function, it is sine of x. So for our chain part, our link, we need to multiply this by the derivative of sine, which is cosine of x. I guess you don't have to use parentheses around it anymore if you have it this way. But again, be careful. If we're going to rewrite this, we don't really have anything in the argument or not, but sometimes having the extra parentheses, 2 sine x cosine x. And that might be good enough. We're not using this derivative to help us calculate other things. But maybe that kind of brings to mind some sort of trig identity from my past. We'll work on it if it comes to if we ever need it, I guess. So kind of be careful. A lot of times if it is helpful to you to name the generic idea of who the outside function is, in my case, it was something squared. I know it's not quite an x, it's something more complicated than x, but if you want to think about it and try to take the derivative, then that kind of helps you understand that the derivative, kind of not a great way to notate this, but I'll say the derivative is 2 times something. So that's kind of where we're getting this part right here. I try not to go too much labels. Eventually you do a lot of practice and you end up not needing to say who's the outside, who's the inside. You kind of just talk to yourself in your mind and then figure it out. But the more complicated it gets, the more likely it's nicer to kind of write little notes to yourself along the way. So let's look at this one. Let me see, I'll separate the page a little bit. We are looking at f of x equals sine the fourth 2x, or the fourth power of sine of 2x. That's a little better way to say it. So again, it's worth your time to rewrite it. Usually when you have these trig, in terms of power, trig functions or powers of trig functions, a little backwards today. So I'd like to see it maybe as f of x equals, this is sine of 2x all to the fourth power. Now, I have to start inspecting this. Things get a little bit more exciting. So I'd like to point out when we go through this and we're kind of looking at it, not only do I see something, I'll even kind of write it outside. There's some outsiders here. I see something to the fourth. Okay, so there's this happening, something to the fourth power. But there's also, I mean, the something is not a little more complicated than x. We actually have the sine of another function that's slightly more complicated than x. So we actually have a couple of outside functions. So maybe I call it outside 1, outside 2. And that's where we're getting sine of something. But I kind of, when I write it this way, sometimes it causes confusion because we really have to deal with, you know, breaking these pieces apart. If I'm looking at the inside of the sine of 2x, then I'm getting the 2x. So you could kind of, you know, have this conversation with yourself in your mind, but you could kind of think, okay, the first step, so by the way, if I can reiterate, there's not one link in our chain, we actually have 2 links. Hence the name chain rule. Kind of clever of them, huh? Okay, so we have 2x and sine of 2x. So here we go. If we're going to take the derivative of this complicated function, I have my derivative notation. I have the outside, the outer part first. So the derivative of something to the fourth is 4 times something to the third. Now remember, it has to be evaluated at whoever was taken to the fourth power. And in our case, it was sine of 2x. Now, before we get there, we're now making a link. There's a chain part coming. Before we move forward, we have to understand we need to look at multiplying this. We have the derivative of the inside function in this case. So the derivative of sine of something is cosine of something, and the something happens to be the 2x. But the issue is trying to figure out, we are still looking at the fact that the argument of this particular function is not just a value of x. So this is the inside part. So we have to have one more link on our chain and multiply this by the derivative of the inside, which is 2x. The derivative of 2x is 2. So now we have our expression. And so let me see if I can rewrite it. These are all factors. Looking at 4 times 2. People will probably write the cosine of 2x at the front part, which would then get multiplied by the sine of 2x. Oh, I should say the cube of the sine. So I'll write it that way. That might be a better way when you're done writing it if you're checking answers. So 8 cosine 2x times the cube of the sine of 2x, if we're going to say that in English. Now, we want to make sure, a lot of times when you're doing the chain rule, you get in the swing of things and you keep trying to add links to your chain that shouldn't be there. So the question always is, how do we know we're done? How do we know when to stop? So I have a kind of a little issue here, or a note of, rule of thumb. We want to never take the derivative of a function that's not in the original problem. That should kind of lead you in the right direction. So for example, kind of if I can go through this part F, because it is a lot more complicated. We're always trying to name all of the functions that we see. So, when we're looking at this, f of x is sine of 2x to the 4th. So the first original function is something to the 4th. That's where I'm getting my outside part. So that's where we see our derivative evaluated at the inside. Now we're looking at taking the derivative of the inside. So if I'm looking at the derivative of the inside, see if I can do this in highlighting. The derivative of the inside is sine of 2x. So if you're taking the derivative of the inside, you are seeing the derivative of sine of something is cosine of something. And finally, the other function we see is 2x. It's a little hard to see if we're trying to highlight it. But when we take the derivative of 2x, that is the inside function, that is going to be the 2. So don't keep going. If you try to take the derivative of 2, which is a constant, you get 0 and your whole derivative disappears. 2 is not a function in the original problem. It is part of the 2x. So I have to caution you to be careful. Don't keep going. Always kind of really decompose the functions you're seeing. See if you can start naming. So by the way, if I'm kind of going through this, outside function, for sure, it's the yellow highlighted part, something to the 4th. The outside subscript 2, it's kind of an outside function to the 2x, but it's an inside function to the 1. So maybe I should really kind of make them kind of standard. It's a little hard to explain. So I guess like sometimes the best way is to jump in and see, who's the outside, who's the inside, play around with some WebAssign and see what happens. So they get quite complicated really fast. A little more excitement coming your way. A lot of times, the more common chain rule problems, you'll see trig functions of a certain variable or expression, trig functions of functions. Power functions also come into play. And then kind of with power, sometimes you'll see some radicals here and there. So we have example 2, asking us to find the derivative. I kind of gave these part A, B, and C just so that we can compare what's going on. So if I'm looking for the derivative of f of x equals 3x plus sine x squared, I kind of note to myself, we don't just have a single function. We are looking at the outside function. So a little note as I'm talking to myself. The outside function is something squared. The inside function, is what is in that base part. The inside is 3x plus sine of x. So if I could kind of decompose them in my mind, I can now start to ask myself the question, if I really want to take the derivative of this composition, f prime x, whenever you take the derivative of something squared, it is 2 times something. And so the something part happens to be what the inside is. So we have 2 times, we have the 3x plus sine of x. Let me write that plus sign a little nicer. I'll give myself more room. See if that works. So one more time, 3x plus sine of x. And then if you subtracted 2 minus 1, you get to the power of 1, so you don't have to write the exponent. But now we're looking at the chain part. So now we're trying to say, what is the derivative of the inside? And if you notice, the derivative, or the inside function is 2 terms, 3x plus sine x. And in each case with these 2 terms, we'll notice that we just have single x's going on. So here's something that would, maybe this type of problem, derivative of the inside would come from maybe section 2.4. So if we want to take the derivative of a sum, we would take the derivative of 3x, which would give us 3. And because it's a sum, I'll include it in parentheses. And the derivative of the next term, derivative of sine of x, is just cosine x. And there's no more chain to add on or link to add on, is because your inside functions only had single x's that you were dealing with. So I don't see a way to clean this up in particularly, and I don't see, I guess, I mean, you could get rid of the colors and maybe the little dot in between, but for the most part, the derivative here, that's all we can do. If you wanted to play with distributing everything out, I don't think it's worth our time. Maybe if we're using it for something else, but let's keep it as simple as possible. Things are complicated enough. Okay, let's play a little bit more. Just kind of looking at my f of x, I'm starting to see a little bit of a trend. I'll kind of notice that the outside function, who's outside the house, that is something to the 5th. And who's inside the house? My inside function is pi x plus secant x. Loving those trig ones, huh? So now, if we want to take the derivative, I'm using the appropriate notation. I'm now going to think about this as, what is the derivative of something to the 5th? And if it helps you, I know this causes confusion later, you can say, like, what if I found the derivative of x to the 5th? Well, I know that should be, I move the 5 in front, 5 times something, and I subtract 1 off the power. Let me give myself a little more room to write, though. So 5 minus 1 is 4. 4, excuse me, not 4th. So, if you're looking at what's the derivative of x to the 5th, that kind of jogs your memory into figuring out, what are you supposed to do with that outside function? I don't recommend this because sometimes it gets a little complicated, but if you do need a memory jogger, go for it. So we have 5 times something to the fourth, and that something to the fourth ends up being the inside. That's pi x plus secant x. So now, because that inside is more complicated than just a single x, we're going to take the derivative of that. And so if I'm going to attach more on, I have to say, okay, there's 2 terms. It's a sum of 2 terms. Both of those terms have just an x. So it's kind of derivatives as usual, so we say. So the derivative of pi times x, we're going to call it pi. And now we just have to go back to trig and say, okay, derivative of secant x, that has to do with the secant x tangent x. And if you were able to derive those earlier in the previous section, that's good. You don't always have to memorize it, but the more comfortable you get with finding derivatives of trig functions where you have them memorized, the better off you are here, and not only here, but calculus too. That's going to matter a lot more that you're faster with this. So reiterating, derivative of secant x is secant x tangent x, or secant x times tangent x. And here, I don't see any benefit. There does not seem to be a way that we would want to simplify this any further. You could get rid of the multiplication symbol. Maybe when you're in WebAssign, you wouldn't have to write that down, but as far as writing it out, we should have our derivative. Okay. So moving a little forward. Part C. I guess I'm obsessed with trig functions today because that's where all my examples are coming from. Please note, if you work on the homework problems, they'll start you off with some normal algebra, and then you'll have a little chance to play with it. But the more comfortable you are with taking derivatives of trig functions, the better off we end up being. So might as well lecture with it. So here we go. We have tangent square of x squared. Again, this is a really good one to rewrite for ourselves. So I would prefer to see this as f of x. Well, it's already f of x. But I'm saying what was being squared, it is the tangent. The tangent of x squared was being squared. So now I'm kind of running into a situation where I'm actually seeing 2 links going on. I've got one of the insides being tangent of x squared. So maybe off to the side if that's something. I also have the next inside. Inside of that, maybe I think about it as a nest if you want to go sideways. I don't know. Whatever kind of helps you. So inside of the tangent x squared is also an x squared. I'll keep the equal signs out of it. We have enough of those already. And I would like to practice trying to write neater. There we go. So now if you're really looking at it, you have the outer, the umbrella, or the house, we say. Sometimes writing and speaking is a little tough for me, but I'll work on it. I have the outside function. So when you're trying to understand who's the outside function, it is something squared. And what's outside that function? If I can kind of do it's kind of a nesting issue. We have the tangent is inside that. And what's inside the tangent part? The x squared. So compositions of compositions, that's a hint. We're going to have 2 links. So let's start. We'll go from here. We're going to find the derivative. So the first thing we're going to look at is what's the derivative of something squared? We bring the 2 around in front. We're going to multiply that by something. So 2 times something, and then when you take a power off, it's something to the first power. That something happens to be the tangent x squared. Now we have a chain going on. We now have to figure out what is the derivative of tangent of x squared. And so we have to go back and say, okay, tangent and secant seem to be related according to derivative speak. So I have to say, okay, first of all, what's the derivative of tangent of something? Derivative of tangent is secant squared of something. And I have to think, what was that something supposed to be? Supposed to be the x squared. So derivative of tangent is secant square, whatever we're taking it, argument. And now we have one more link for our chain. We have to say, what is that inside function? How do you take the derivative of x squared? Well, derivative of x squared is 2x. And we stop. We do not see a 2x in our original function, so we don't keep calculating derivatives like crazy. So you got to be really careful and know when to stop. That's kind of a big part of mathematics too. Sometimes, like, you guys know all the stuff, but you have to have a clear distinction. I know enough, so I know I'm done with the problem. Now, if we want to clean this up a little bit, sometimes, web of science is not too happy with all these parentheses and these extra powers of 1. I see 2 factors that are monomials, 2 times 2x. So that gives me 4x. And then here, the rest of it's not so exciting. We would just say it's tangent of x squared, but that's multiplied by secant square of x squared. And I suppose you could play around with some trig identities at that point, but not worth our time if we're just calculating derivatives. If the directions specify, write your function in terms of cosines and sines, or write it all in terms of tangents, well, then I think that secant square can kind of be useful. I think that Pythagorean identity comes back into mind. But at the meanwhile, let's just keep it the way it is. So we have 2 links, and now we'll end our section with something slightly more exciting as we go. So part D, we have f of x equals the cube of secant, and then we have to think about, oh, there's a cosine, and then there's a 2x. So if I'm thinking how many trig functions are really involved here, I could kind of go out on my side. I have like super outside function. I know I have, well, if you want to rewrite it, sometimes we start getting used to this. But I can tell anytime I have a trig function, I know that that would be secant of whatever I'm taking. I'm gonna have to use a little bit more different types of parentheses and stuff. Secant to the 3rd power, or what is it, the cube of secant. And maybe because there's extra parentheses, I'm looking at maybe sometimes color coding them or writing them in different sizes. So I have secant of cosine of 2x. Sometimes that makes it stand out so you can see. So now if I'm kind of labeling my outside, I kind of go off to the side. My super outside function is something to the 3rd power. Now I notice that something is not just a nice single x. So if I'm going to take the derivative, there's chains involved. It looks like there's 3 functions involved in this composition, so that's where the 3 links will come from. But I'll start. Let's take the derivative of the outside. So that becomes 3 times something squared. And if we're interested in changing up parentheses and brackets, if I need to, I kind of find a need to. I'll rewrite them as brackets to kind of help with some of the visuals here. So now remember, the inside part, still the same. All we're doing is looking at secant of cosine. Maybe I'll alternate the colors just so that I can see what's happening. So secant of cosine 2x. Now, if we take this portion right here, we'd be kind of referring to what's the inside of this part. So if you kind of say it's secant of something, then we have to think about, okay, what's the derivative of secant? And off to the side, if you needed a little bit of trig help, you could kind of maybe think off to the side. If I want the derivative of secant, you can't see the little prime there. Here we go. So it's a little note to yourself. Okay, derivative of secant is secant x tangent x. But I know when I try to find my derivative of secant of another function, I just have to make sure, we'll play with this here, the link to the chain, I'll do my best. It's gonna be a little longer chain. It's not just secant x tangent x, it's going to be secant of cosine of 2x. So there's the secant x part right there. Multiplied by tangent of cosine of 2x. There's the tangent x part now. So that's our first link. The next thing we have to look at, and we're gonna go a little bit more writing in the horizontal direction, so be prepared for that. And sometimes as you're going through this, if you make a little mistake, it throws off the entire problem. So, take your space up on the paper. Feel free to tape extra papers on. I know it doesn't quite fit into a notebook, but you know what? It's better than getting the problem wrong. So take your time. Okay, so I want to go and address, I want to look at the inside of this inside. So I'm kind of thinking about the nest. What was inside the secant part? Who's the argument of the secant? Well, in our case, the argument of the secant is cosine of something. So this is where my next link comes from. So I have to think, okay, what is the derivative of cosine? And we know the derivative of cosine is negative sine. But it's not just negative sine of x, it's negative sine of something. So maybe I'll kind of use the kind of color code my inner arguments together. And so then we have to think about, what was that something? What was the cosine evaluated at? Cosine was at 2x, so the sine should be at 2x. So the derivative of sine is negative sine, but then it was more complicated than just an x, so we had to write the 2x in the argument. And now, my friends, we have one more to go. One more link, because if we keep playing, I'll have to put this in orange or something. Might be the inside of the cosine was 2x. So the derivative of 2x is just a 2. And now, my friends, we are finished with the calculus part. Now it becomes a game of algebra. So if I can I got to shrink it down a little bit so we can see this a little better. I'm going to just rephrase this just in case. So as we were going through this, we're kind of keeping attention to our inside. So notice once you took the derivative of the outside, the next step was to chain or tag on the link of the derivative of the inside. So these two derivatives go hand in hand. So the derivative of the yellow part on the left, before you're taking the square, is secant x tangent x in terms of a different argument. Then kind of looking at the arguments of the secant and the tangent, and I'll go underneath because it kind of highlights that. Your job is to take the derivative of the inside so that that's the second link on your chain. So that's where this is coming from. And then you know you need an extra link because that argument of whatever you wrote, it's not just a single x, it's a 2x. So that's where this derivative is coming from. So we are now finished with the calculus. Sometimes, I don't know if color coding works. If we take our time here, we really want to analyze who's outside, who's inside, inside, inside. And you can kind of see where I wrote my nest just to kind of keep my thoughts in line. There's a lot of bookkeeping involved here. So here we go. A little bit of algebra left for us. If it is worth our time, you may be interested in saying, okay, let's maybe look at if we see any number factors. It's a little bit playing with algebra. I think I'll open that up a little bit so we can see it a little bit better on the video. So we've got 3 times 2, that's nice, that's 6. And I suppose there's some steps I can skip, but sometimes it's beneficial for me to understand that when I see the secant of cosine of 2x taken to a power of 2, maybe it's beneficial to rewrite it in its normal form again. And if that helps us, we could just rewrite everything. I got to make sure I have all my parentheses involved. And while we're here, as I'm going through this, I can get rid of the negative part. I can put that out here. So let's put that right there. That way we don't have extra set of parentheses. So then what I'm kind of looking at is I'm seeing, all right, well, I do see a secant square, another secant, and they both have the same argument. So it looks like using exponent laws. Whenever you multiply with the same base, you keep the base and add the exponents. We should now get -6. And then it's probably better to rewrite it as secant with a cube of cosine of 2x, still multiplied by tangent of cosine of 2x, and still multiplied by sine of 2x. And maybe there's some justification for using some identities here and there, but at this point, since we're not doing anything with the derivative, we're not trying to use it to calculate anything else, this looks like as simplified as it can be without stressing ourselves off. So that, my friends, is a grown-up derivative. So don't worry, they're not going to hit you up with that in the first problem or something. We have to work our way up there. So kind of take your time, absorb it, practice, 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 and I will see you next section.